Now let's take a look at a few practice examples using circular motion. Number 1 is that a merry-go-round takes 30 seconds to circle around once. That means that our period is going to equal 30 seconds. We're told it has a radius of 3.2 meters, and the child has a mass of 16 kilograms. We want to know what force does this child feel. So we're simply going to say, all right, we know what is going to be the net force on the child, and that will be our centripetal force. Our equation for that is 4 pi squared mr all over t squared. So let's plug in the variables that we have. Fc will equal 4 pi squared times 16 kg times my radius of 3.2 meters, all divided by 30 seconds squared. When you go through and calculate this out, we find that the centripetal force is simply going to equal 2.245 newtons. Now, one of the questions I asked you to solve for homework tonight wants you to do the same thing, only instead of using 30 seconds, I want you to cut that time in half and instead use 15 seconds and see what kind of effect that has on the child. Now, in the second part of this problem, I asked what is the acceleration of the child? Here we simply know that force equals mass times acceleration. My centripetal force then equals my mass times my centripetal acceleration. So 2.245 newtons would simply equal 16 kilograms times A. Calculating that out, we find that the acceleration is simply equal to 0.1403 meters per second squared. Now this brings up an important point. We have this object that's moving at a constant speed, but it has acceleration. It has acceleration because it's changing directions. And that's why an object moving at a constant speed going in a circle will end up having a net force acting on it and a net acceleration. Okay, let's take a look at one more example, and this one takes a look more at what's going on with this net force type of thing. So I say, okay, I'm going to place a cup on a flat board, and then I want to spin it around my head in a vertical circle. So I'm going to literally be standing here, and we'll do this as a demo tomorrow. Apparently I have a small head. And I'm going to take this, and I'm going to spin a cup up and around. So that's the pathway it's going to take. I want to take a look at this cup at the bottom of its swing. So we know it's coming in like this and leaving like this. And here's my cup. Okay? Now, we have multiple forces acting on it. The forces that we're going to see that are acting on it are a normal force upwards and a force of gravity downwards. Now, I didn't draw in an centripetal force. The reason is because, as we said earlier, centripetal force is going to equal that net force. So centripetal force here is simply going to equal my force normal minus my force of gravity. Now I did that. I did normal as positive and gravity as negative because normal points in the same direction up as my centripetal force at this point, remembering that centripetal force points towards the center of the circle. So let's go through and see if we can solve for what the normal force actually is going to equal. Okay, so I know centripetal force can be 4 pi squared mr all over t squared. I'm going to set that equal to normal force minus mass times gravity. Now, we may run out of time before this actually finishes, but from here, we're simply plugging in variables. We know it's going to be 4 pi squared m, which is going to equal 0.8 kilograms. I forgot to put that in the problem. It's a 0.8 kilogram cup, 0.8 kg, and try to go from there.